I'd like to just backtrack for a moment. I forgot to mention when it comes to the algebraic observability theorem that once again MATLAB has a function to calculate this observability test matrix for you. And before you put away your computer, can you just check for us again? I think it's OBSV, but I'm not 100% sure. So once again, you throw the A and the C matrices to this function in MATLAB, and MATLAB will then calculate the N matrix for you, OBSV. Okay, so you can use that to then calculate the N matrix for you when you need to test whether a system is observable or not. Okay, so let's then carry on with the next topic in chapter 5 of Friedland, and that is the topic of disturbance and tracking systems. Now, I think right in the beginning when Friedland introduced the state differential equations, he mentioned the possibility that you may have disturbances. And he then also, at that time already, showed this alternative form of the state differential equation, where of course the A and the B matrices has the same meaning as before, but where you have another matrix, the F matrix, pre-multiplying the disturbance state, X sub D. So X sub D may be he actually made the point at the time that X sub D, you can think of X sub D also as an input to the system, but it's an input that you don't have control over. It's an input coming from some other disturbance. And so you can have a single disturbance. In that case, the F matrix will be a column vector of having the same number of rows as the A matrix. Or of course it can be more. You may have more than one disturbance. If you have two, then the F matrix will be having two columns. He also mentioned at the time, I think, that you can think of this X sub D as a so-called exogenous input, an input over which you do not really have control. So when we deal with disturbance systems, it is then fitting to write our state differential equation in this form. He now also introduces another aspect, and that is of having a tracking system where XR is then the state that you'd like to track. So initially, we'll get to another case a little bit later today, but initially you should think of XR as a state vector really having the same meaning as X. In other words, XR is a vector of, firstly, of the same length as the X vector, and where the elements in XR has exactly the same meaning as in X, except that this is the state you'd like the system to track. Now, of course, the system will only track it if it's a perfect control system, and one doesn't get that. So there will be a difference between the actual states of the system and the states that you'd like to track. So this XR can be a function of time. If you think of something like a step, if you'd like the states to track a step, then it means that it's actually a constant function after the step. And when we're going to, in this module, work with the tracking signals, we'll normally work with steps. But okay, don't worry about that too much for now. For now, think of the tracking signal as a vector that changes with time, and it's really the states that you'd like the system, it's like the time functions that you'd like the states of the system to follow, to track. And so he's then going to, in his further discussion here, use these two differential equations, which are rather, in my view, not only rather arbitrarily, but yeah, there's not really a logical explanation for why you would use these additional two differential equations, other than it's convenient to, if you use these differential equations, it's convenient to show what he wants to show. It's convenient to use this to bring the theory to a certain point where you can then further on use it in a practical sense. So what he is assuming here is that the first time derivative of the disturbance is a coefficient matrix A sub D times the disturbance. So it's almost as if he when we look at this equation, we think of the disturbance not as a state but as an input. But when you look at this equation, you think of the disturbance as if it is actually a state, an additional state. And then one which is described by this differential equation. Now, if the disturbance is something like, if you think of an aircraft system, something like gusts are normally considered as disturbances to an aircraft system. And it's not really true that for a gust, that the time derivative of the gust will be somehow the coefficient matrix times the gust itself. So there's not really a physical argument that you can raise for justifying this assumption of this differential equation. Likewise, there's not really a good physical argument to say that the tracking system time derivative, not the tracking system, the tracking signal time derivative will be somehow the coefficient matrix times the tracking signal itself. But let's humor him, if I can call it that. Let's humor the author and see where he takes us with these two equations. Okay, so he then defines the error state vector, which is the difference between the actual state vector and the tracking vector. So you should think of this as that this XR is a time function that we would like the system to track. So it's known. It's a known time function. And of course, X will be the actual state vector. And then the difference between the two. But please note the way that the difference is now defined. It's defined as the actual state minus the tracking state. That is then defined as the error state. So this E then is also a state vector of the same length as the actual state vector. Now with this then, you can recast this differential equation into his equation 540, which really says that the time derivative of the error state is the A matrix times the error state plus the E matrix times it's a different state vector x0, where x0 is it's a column vector. Of course, here it's written now as the transposed of a row vector. In other words, the upper part of this column vector is the reference state vector, and then the lower part of it is the disturbance vector. So if you have got a single variable for the disturbance, it will just be one value, but otherwise, like over here, this xd can, for instance, be a 2 by 1 vector if the disturbance has got two elements. So in that case, the bottom two variables in x0 will be the two disturbance variables. So this x0 state vector is then the exogenous inputs, but he considers them as states here, and so they are then. So this vector is then pre-multiplied by the E matrix. Now I've said that they are states, but they're not states in the sense that the E matrix will be a square matrix. So you can see that the E matrix then is actually the A matrix minus the AR matrix. It's the first sub-matrix of the E matrix, and then the second sub-matrix of the E matrix is the F matrix from the original equation. So it's just a matter of taking to prove this, it's a matter of taking the time derivative of this definition of the error state, and then substituting on the right-hand side. Once I've taken the time derivative, I'm substituting the x dot with the first equation and the xr dot with the second equation. So you can work through that and convince yourselves of this. Okay. He then defines a meta state let me just backtrack. Further on, he's actually going to work, and if we get to chapter 6, when we get to tracking systems, we're actually going to work further with this equation 540, using the definitions at the bottom of the slide. So, and we're going to do that without using the meta-state stuff that is discussed just after that. So just keep this in the back of your minds for later today. But in any case, then the meta-state is introduced here because sometimes things are analyzed in terms of this so-called meta-state. So the meta-state, he uses a bold X. I think he uses a bold X for that. Just make sure about that quickly. Yeah, he uses a bold state for the meta-state. So this is also a state vector that which I've now expressed in terms of the transposed of a row vector. So the first part of the state vector is just the error state, and then below that is the state of the exogenous variables. In other words, if I go back to the previous slide, this x naught, as it's defined here, which was a column vector, that it's as if you append this x naught vector to the x state vector. That really gives you the meta state, bold X. And this allows you to actually write the whole system of the original state vectors plus the reference state plus the disturbance states. As that combined gives you the meta state vector, but you can also then write your differential equation as x dot ax plus bu, in other words, in the standard form, and y, the output of the system is cx, where of course a, b, and c now has different meanings from before. But essentially what I'm doing here is I'm recasting this equation of 540 into this form of the with a meta state, and so he doesn't take it any further in chapter 5. He gets back to that later in the book. But please take note, he does mention this, that the meta state is uncontrollable. So if you work in a scenario where it's a requirement that you need to have a controllable system, then you cannot follow the approach where the meta state is used. Okay, and I think that is the conclusion of his chapter 5. And with that, then I'd like to, well, maybe I should just ask, are there any questions? Okay, so then I'm going to stop the recording here.